Of London Futurists, in between my career, which has been in smartphones and in mobile computing for the last 25 years. But I've been organising these meetings in London on futurist topics since March 2008, and I'm glad to see this growing interest. So the reason the London Futurists exists, we talk about the future. It's not in the next 18 months or the next 2 years. We're not so interested here in what's going to be in the iPhone 6 or in the next version of Android. Fascinating though that is. We're looking a little bit further out and looking at what might be the case for, say, 3 to 40 years. 3 years may sound too soon. I do believe, in fact, that in the next 3 years there's going to be at least as much change as possibly the last 5 years, even more. And there's quite a lot of change even in that time. So I'm looking at, and the speakers I invite are looking at actually quite radical scenarios for this short to medium term timescale. And I say radical, I mean not just more of the same, not just a little bit different from what we've had in the past. The possibilities are that sometime in that period, we're all going to say, my goodness, I really wish we'd seen this coming. This is so different from what we'd expected. You know, this is a drastic change in the history of society. So I want to encourage serious analysis of these radical scenarios. And you can see it's scenarios plural. I don't believe there's just one possible future by any means. I think it's quite open as to what will happen. But we're here to bring in thoughtful speakers. I'm quite keen on the entertainment side too, and it is a fun topic, but in the end it's also a deadly serious topic, because as well as there being potential upsides of the technology and the other changes, there are lots of potential downsides. So that's why it's a serious topic. The biggest driver for change is the technology. And more and more people are working on technology. Technology is feeding off itself. Software helps write better software. Software helps allow nanotechnology to be more effective. The nanotechnology in turn can find out what's happening inside people's brains more effectively. We can understand how the brain works. We understand how the mind works. We feed that back into the next version of artificial intelligence. And there's a strong cycle. So that's why I believe the technology change is accelerating. But it's not all good news by any means. I think in the medium term, near to medium term future, there are many crises. And I often have speakers here who talk about some of the big downsides of not only of technology, but of the other changes. The other trends, of course, are in society. I believe that in order to take best advantage of the technology that's coming without it causing a crisis, is going to need a lot more collaboration, a lot more pooling of insight and building better solutions collectively. And lastly, I believe that it's a matter of, in many cases, changing how we think. There are a lot of the philosophies which we've grown up with, philosophies which have served humanity fairly well on average, are no longer really fit to cope with some of the challenges that the new technology and the ever more connected world put our way. I believe, this is my personal view, that we need to sort of move from a set of philosophies which we might be called humanity 1.0 to, call it humanity 2 or humanity plus. And just to spend a moment spelling out that difference between the humanity constrained sort of view and a more humanity enhanced view. The constrained view says, well, actually, we're short of things. You know, we are running out of oil, we're running out of food, we're running out of fresh water. You know, it's a real hassle. Because of this, we have to live in a very economically minded way. We have to take account of profits in order to decide how to allocate things in society. Whereas the humanity enhanced view says that, in principle, technology and other means will give us much of what we need. In fact, more than what we need. This is the abundance mentality. And of course, tonight's talk is all about not just abundance, but even radical abundance. And this is more of when there's more resources around, there's less focus on competition, there's more ability to share and to collaborate. The humanity constrained view, or humanity minus, often looks backwards to a golden age. Or things were much better when things were simpler, when there were fewer people on the earth messing things up, when we didn't spend all our time watching cats on YouTube or trying to follow Justin Bieber on Twitter. You know, we had a better kind of culture. That's the kind of viewpoint. And this kind of viewpoint is fearful of progress, whereas the humanity plus viewpoint, the viewpoint which I think deserves a lot more exploration, looks at a golden age potentially in the relatively near future, and it encourages intelligent embrace of progress rather than fighting against it. The humanity-constrained view you often hear is, well, we mustn't play God. You know, if we play God, we're going to mess it up. We should leave God to play God, as it were. Whereas what I'm advocating and trying to encourage in these talks is a view of, well, there are godlike powers coming to our hands, and if we don't use them wisely, those of us who think hard about it, then probably other people will use them less wisely, and it'll be awful. The humanity-constrained point of view looks at sort of, well, we hope that we'll have enough. We hope we'll be well. We expect in the end we'll personally decay. That's a shame, but that's how it is. Whereas the humanity plus view sort of says, well, actually, we can live better than we've ever done in the past. We can live better than well, and we can look forward to rejuvenation. We can look forward to personal vitality. And lastly, I summarize a lot of this humanity-constrained point of view. In the end, it's sort of a sad, defeatist approach. We do the best with enough, and then that's the end. Whereas the humanity-enhanced view, taking advantage of the new technology of one sort or another, is a more inspirational approach. So where do individuals come in all this? With all the technology trends, the trends in change in society, are we just spectators in this? And I avidly think not. I'm very much in favor of all of us here taking some personal responsibility. We can get involved researching possible futures. We can get involved engineering solutions. And if engineering isn't our particular forte, we can get involved in business, making connections, taking advantage of the profit motive where appropriate to encourage more rapid development of good solutions. And some of us can just be good old-fashioned activists, hustling for things to change, hustling indeed for other things not to change. We can spend time as communicators. If we aren't expert engineers, then at least we can communicate what the engineers are doing and what they could do. We can become bloggers, we can become journalists, we can become educators, we can become teachers. We can get involved not just communicating the kind of bare bones, the facts, the rational argument. We can also get involved in putting a positive view of the future through artistic work, advocacy and critical thinking, and last but not least, the visionary view. So that is what I'm trying to do in these meetings. And although I've said this is what individuals can do, I believe that we as a community, we can all help each other to be better involved in playing our roles. We can discuss with one another. Actually, I'm strong in engineering. I've got this business idea. I can see how to build a film about it. And together, as a community, we can actually make a big dent into making it more likely that we're going to see the upsides rather than the downsides. Paul, you want to ask a question now, yes?
There's one role missing from your list of roles that are useful for the future. Donor.
Donor, yes.
A great deal is done by people whose full-time work is in thinking about possible future scenarios. People who pay their wages do an enormous favour, potentially do an enormous favour to our future.
Yeah, so donors or sponsors or fundraisers of one sort or another. So if you want to donate, go and see Paul. I mean, there are of course many projects that do indeed need that financial investment. So what are we doing here in particular? I just want to spend a couple of moments before I hand over to Eric Drexler as the main speaker, talking about some of the other meetings we've got lined up in the next 6 weeks or so. When we talk about the future, lots of people shrug their shoulders and say, you know, I was promised flying cars. I was promised jetpacks. It hasn't happened, you know? This futurism stuff's all bunk. Well, actually, we've got a speaker lined up on the 6th of July. He's not quite going to talk about flying cars. We're going to talk about driverless vehicles and about how this is quite close to happening. That's Nathan Coren. Is Nathan in the room? Yes, indeed. Right. So if I get any of this wrong, Nathan, you'll correct me, yes? Fine. So Nathan's actually an engineer in many ways. He's got involved in creating some driverless vehicles at Heathrow. And he's also involved in consultancy with many of the cities of the world where, frankly, the current urban transport system's a real mess. You think it's bad in London, it's much worse in many other countries. And you can't just, however, roll out the technology. You've got to change the infrastructure. You've got to change a lot of society and society's expectations. And so Nathan's going to be leading a session on the 6th of July about that. So we can see where the future of transport's going to go in the next 5 years or so. 5 years. Another thing people say, well, I was promised robots. Where are the robots? And is there any robots in the audience, can I ask? You're a robot, right? Well, there is a conference in New York. Now, this is a bit more complicated, so this isn't my conference, but I want to have a meeting here, London Futurists, to report back on what happened at that conference. So this is a conference organized by the 2045 Project. They are actually founded by a very interesting Russian entrepreneur, business leader called Dmitry Itskov. I think, Yana, you've met him, haven't you? Yes? And so he has had a vision that, in the future, humans and robots will merge. And they'll merge in stages. And he says, there'll come a time when our physical bodies are kind of ill-equipped to look after us, and wouldn't it be nice to have a robotic body instead? A little bit like in the film Avatar, indeed. And he envisages 3 phases in which this might happen. Avatar A is when you stay in your own body, but somehow there's a connection, a brain-computer interface to drive robots around. And then part 2 is you actually take the brain out of your body and put it inside the robot. And that's a bit scary. And part 3 is even scarier, because you take the mind out of your brain and you put the mind into the robot. And so he has got a lot of people looking at his ideas, and some of them are saying, well, and then he says, well, it's 2045, a lot might be possible. So a lot of people, and you can see some of the names there, Marvin Minsky, one of the pioneers of AI, Ray Kurzweil, one of the pioneers of singularity thinking, and so on. They will be at this conference, and I will be trying to distill some of the interesting stuff from these 2 days and bring it back here and share it in 2 hours. So, of course, I'm not going to get all of it. Rohit, yes?
We have a free place to give away to the conference. So
You have a free place to give away to that conference?
We've done a deal with them. So, 2 things. Anyone who wants to go, you can get a 20.45% discount.
20.45 discount, yes?
Right until the start of the event. Talk to me afterwards until you get it. But we also have one free place if you can get yourself there.
Yeah, so you've still got to fly to New York and pay for hotel accommodation in New York. Though Brian did find a quite cheap hostel, yes?
Gosh, yes. Manhattan is a bit frightening on the sticker shock of, what? I just want to sleep. I need is 2 square meters.
Well, anyway, so...
Very simple way of putting your name into the draw for it. So if you're interested in going, just see me afterwards and I'll tell you how you can win the free place.
So I think with the people who are there will be some interesting topics. Whether or not we actually get round to the idea of moving a mind into a robot, I think there are some of the world-leading experts, David Hansen and Hiroshi Ishiguro, on actually creating human-like robots. Some of them will be demonstrated. There will also be people there who are talking about what can we learn about how the mind really works, because we can probe more and more finely. We can have nanoprobes. Maybe they're not quite nanoprobes yet, but they're smaller and smaller probes into the brain, and you can sort of almost see consciousness working. And so there'll be some insight in that. And then there'll be other people who say, well, we can have immortality, but not by putting our brains or our minds into a robot, but by other means of rejuvenating the physical body. And I think Ray Kurzweil might talk about that. Ray Kurzweil's talk is actually called Immortality by 2045. So some of it, no doubt, will be disappointing. Some of it, I hope, will be illuminating. And if you can't make it to New York, it is quite an effort, then hopefully I and maybe Rohit, if you're there too, we can and pool some of the ideas together. So that's in, 3 weeks' time. In 1 week's time, if you can't wait, also in this building, in this university, UCL, but in a different building, we have another eminent futurist. He's from Venezuela, Jose Luis Cordero, and he is a professor of the Singularity University. He's been spending a long time thinking about issues such as new forms of energy, taking advantage of synthetic biology, the convergence of different technologies, nano, bio, info, cogno, and he's also been thinking about artificial brains, healthy lifespans. He's going to give a talk in this series, London Futurists, in a week's time, which he will cover what Singularity University is doing and what these other trends are possible. It's quite a lot to cram into 2 hours. If you think it's too much for 2 hours, well, the good news is he is also doing an 8-hour-long version together with Rohit the following day. Now, this is a £95 price on this. This isn't a London Futurist event, but I thought I'd mention it. It's organised by Fast Future, and he will look at more length. And that won't be a big room like this with nearly 100 people in it. That will be limited to about 20 people. So they'll be more intimate. So I think last time I checked, there was 1 or 2 seats still available for that. But it's not going to be a huge room because the goal is to have more opportunity for one-on-one discussions with these futurists. The last thing I'll mention before we'll feed you all day long too, yes? With futurist healthy food made of nanoparticles. Right. And then the last event I would like to mention, it's also not a London Futurist meeting, but since I was talking about living longer and through different means, would like to mention SENS. So SENS has got a 4-day-long conference in Cambridge, in Queen's College, Cambridge. And the organizer of SENS is here, actually, Aubrey de Grey, sitting in the front row. And he does these conferences once every 2 years. So if you miss this one, you've probably got 2 years to wait. You don't do them in an accelerating schedule. Isn't that, yeah? That? Well, anyway, so that is a 4-day-long conference, 5 days long, yes? Lots of very serious talks there. So some of them will be very technical indeed. They'll go into details of genetics. But I think, I'm going to go there, and I'm sure half of the talks will go over my head, but I'm sure I'm going to get a lot to think about. And I mentioned some of the speakers there. There's George Church, who's one of the leading synthetic biologists in the world, Alexander Zavonkov, who's written a book also about how there's going to be a takeoff and a new global economic growth based on the rejuvenation technologies. So, if you want to find out more about that, you can Google SENS 6 or come and talk to Aubrey afterwards or talk to me. So that's some of the things that's going on. So with having said that, back to tonight, we're going to open up now for Dr. Drexler to have a session sharing in details of his book. You may have noticed some of his books are on the table. There's, a few left. So if you haven't got a copy yet and you're sufficiently interested at the end, you can get them at the £5 discount from Perseus Books. Most people will then have to go, but if some of what was discussed was sufficiently interesting, then a group of us will be doing a 2-minute walk down Torrington Place to the Marlborough Arms. And having said all that, I would now like to introduce Dr. Drexler. So, I don't know, how many of you read at least a little bit of this book, Engines of Creation? Well, that's quite a lot. How many read a bit of this and said, wow? Yeah, this is a fascinating vision of the future. And this book came out in 1986. I read it in 1990. How many of you have thought in the meantime, well, whatever happened to nanotechnology? You know, I was promised robots. I was promised flying cars. I was promised nanotechnology. Where's it gone? Well, we're going to find out tonight. What? Yes, Graham? Sense. So why hasn't nanotechnology, but maybe it has been here, maybe we're looking in the wrong place. So Dr. Drexler has been writing this book for quite a while. It's a huge amount of information, fascinatingly written. I haven't read all of it yet. My wife has read all of it, and she's not deeply technical, and she loves it, thinks it's very clear, very compelling, and every time we drive anywhere now, she's telling me about some part of it. So it is gripping. I have read about a half, and I endorse it too. But who better to tell you about it than Dr. Eric Drexler?
Thank you, David, and thank you for organizing this meeting and inviting me to be here to lay out what I sometimes think of as a banquet of indigestible truths. So, we live in a unique time in history, as people often say, and in one way in particular that I would like to highlight, which is that now we understand matter. We understand what this stuff is. We understand what nuclei are, electrons are, and how they behave. Sometimes the complexities lead to an inability to predict what will happen, but engineers are very good at finding circumstances in which the complexity is well managed. We see integrated circuits with billions of nanoscale parts working at billions of cycles per second and behaving in, at the functional level, a perfectly predictable way, because engineers, without understanding everything that there is to understand about semiconductors, have chosen the set of materials and conditions and operations that actually work in a predictable way. We have an opportunity today to do something similar in the molecular world with mechanical devices. We have a nanosystems technology of nanoelectronics. We do not yet have a remotely mature nanosystems technology of nanomachines. Physics tells us very clearly that such a technology can exist, that it can work, and tells us some of what can be accomplished by means of that technology when we have implemented it. We live in an unusual time in another way, which is that we not only know what matter is, but we know how to organize the atomic building blocks of matter with atomic precision in a wider and wider range of circumstances. This graphic outlines some highlights on the path to where we are today in this area, starting with organic synthesis. This molecule urea, very few atoms back in 1828, and proceeding through steps in understanding in quantum theory and accomplishments in moving and organizing atoms up through the million atom scale of atomically precise structures today, beyond what Paul Rodemund demonstrated in 2006. Structural DNA engineering has come a long way. You noticed with respect to the upcoming meeting in New York, George Church was one of the names, George Church of Harvard. He does a remarkably wide range of things in research, and structural DNA nanotechnology is one of those. So the question arises, where is this leading? Where can this lead? We've seen progress from small molecules to large molecules, a wider range of structures in a qualitative sense. But where can it lead if we apply engineering methods to these technologies and move forward in a focused way, using tools to build better tools? If you look around yourself today, you see, people, and pretty much everything else was made by or with the overwhelming help of a machine. Well, where did the machines come from? Well, they were made by or with overwhelming help from other machines. And those machines, well, they were made with the help of machines that go back yet another step. And if you trace to these, these are the leaves of a tree. If you trace back to the twigs, the branches, and to the trunk, eventually you find the machines that are used to make the machines that make the machines that make the machines. Central to that are machines made of steel that cut precision steel parts that can be used to make precision machine tools. When people make semiconductor devices, they use large macroscopic structures that are made by this kind of technology. Well, where did those machines come from, the ones at the core of our physical capital structure? Well, they were made by earlier machines, made by earlier tools, people using earlier tools. And if you trace that back through the generations, you find at some point, maybe halfway back, a blacksmith hammering away on a piece of iron with a hammer and an anvil and tongs. And blacksmiths from time to time learned to make better hammers and anvils and tongs, and to make more precise structures, and to help build clockwork machines, and machines that could grind and cut with greater precision, eventually on a path that led to the Industrial Revolution and where we are today. So the core of technology is tools that can be used to build better tools. That's the basis for fundamental progress in what we can do with the material world. There are many other areas that have a certain autonomy to them, but there is an angle of view in which this is from which this is what's fundamental. Long ago, at least it seems to me long ago, a number of decades, when I was at MIT, I was reading the literature on molecular biology while I was studying space systems engineering. I felt it was wise to try to understand what was understood about the world. And there was talk of molecular machines in cells. I looked at this, largely made of protein, and asked, well, that's very nice, but can we learn to design and build machines of this general sort ourselves? And I concluded that, yes, that ought to be feasible. Genetic engineering was just beginning to take a good, firm grip of capabilities at that time. This was in the mid to late 70s. And the question was, well, could you engineer these protein molecules, given that you could make the genes required to synthesize them? The answer seemed to be yes, and then I asked, what could you build with the machines that you could build of protein? And the answer is things that aren't made of protein. And what could you build with those machines? Well, a wider range of structures, better materials, stronger, faster. And if you follow that spiral of progress, you're led to a technology which is the one that I will be outlining today, which I have described, labeled as atomically precise manufacturing. Now, in 1986, I introduced a term and a concept of nanotechnology. People ask me, what does what nanotechnology mean? My answer is it doesn't mean anything in particular today. At the time, it referred to a atomically precise manufacturing technology. Since then, it has come to mean swarms of little tiny robots that might nibble your toes and eat you, or material science. And so people have been asking, where are these inevitable, dangerous, wonderful, magical robots? And the answer is, well, you know, that's not what anybody wants to build or needs to build or is working on. And they've looked at nanotechnology with its billions of dollars of funding, in multiple billions in multiple places around the world, and said, well, where's the progress toward any kind of molecular or atomically precise machine technology? The answer is, they're working on material science. The label got applied to something else, and if you focus on that field, you're not going to see substantial progress. Some steps that contribute to progress, knowledge that's helpful, some materials and structures, but not the central progress. That's in the molecular sciences, and it's mostly not called nanotechnology. So what I outlined a moment ago was essentially a technology trend, a trend towards size and greater complexity and higher performance in molecular structures. And that raises a question that I think it's useful to talk about in the context of futurists and methodologies. The question of what can one know about future technologies? What can one know with confidence? Well, it depends on what questions you ask, and asking the right questions can make a large difference. If you're trying to predict scientific discoveries, genuine discoveries, well, that's logically impossible, because if you could predict it, you'd know it, and if you know it, it wouldn't be a discovery. So there's something strange about trying to predict a scientific discovery. Sometimes you could say, we'll find out what the answer is, but you don't know the answer. Well, one might also try to predict specific technological developments or specific winning technologies. And there are problems with those too. In specific technological developments, well, new science might come along, and there are also unexpected inventions. And if you're trying to predict what technologies will win in the marketplace, well, if you're good at that, you can make a lot of money, stock market. But it's unreliable. You can't predict what companies are going to do, what the competition will be, what else will be invented that will compete with the wonderful device that you think is good. So those are the usual questions that people ask about the future of technology, this kind of question about actual future developments. But there's another kind of question. And those are the questions that one answers in exploring the potential of technology. And that has nothing to do with time. The potential of technology depends on the structure, the nature of physical law. Physical law describes causal relationships. What configurations of matter, what initial conditions will lead to what results. It describes the falling of a rock. It discusses the computation in a computer. It describes the computation in a computer. It defines the potential of all possible technologies, past, present, and future, in principle. These are a fixed part of a landscape of technologies that's the same today as it was 1 billion years ago, and it will be 1 billion years in the future. So one can study the potential of technology without saying anything, in principle, about the future, because it's a study of nature, or the building artifice on nature. And so if you ask the right questions and apply engineering methods and knowledge of physics, it turns out that you can find some answers to questions. You apply textbook physics and engineering principles to suitably chosen physical systems. You get answers of what the behavior will be, and you can check the numbers. So that is the basis of the work that I've done. It's one area of enormous misunderstanding. People say, well, you're talking about the future of technology, and it's beyond what we're doing, and it's high performance. You must be making non-conservative assumptions, and no one can know. Well, in fact, you can know. If you had this structure and applied torque to the shafts, standard molecular dynamics methods tell us, that are good enough to tell us, that you'll get gear behavior, shafts and gears. They're not like shafts and gears, they are shafts and gears. Shafts and gears are defined by the structure and the function, and these have that kind of structure and that kind of function. It just happens to be the case that standard methods used in computational chemistry all the time are very well adapted to describing this class of structure. which on the other hand is very poorly adapted to being fabricated today. Chemists can't make this kind of thing because we haven't built the tools to build the tools to build the tools that could make these things. But the intermediate steps are rather well understood. So if you understand components, you can put components together to build systems. This is what engineers do on paper and when they have the tools in the physical world as well. And as I was saying, a conservative analysis can yield high confidence results. Engineers don't care exactly how strong something is, they want to know that it's strong enough. And so you don't know exactly how strong some particular structure will be, but you make it twice as strong as it needs to be, your errors are 20%. You say, good enough, and move on to the next component. And with a sufficient range of components, in electronics, it's conducting paths, transistors, and capacitors, thinking of what's on a chip. And with those and some variations of those, you can build digital logic systems. Mechanical engineering isn't quite as simple as ones and zeros being shuffled around. But nonetheless, there's a certain set of components that's enough to give a sense of what can be done. Motors, shafts, bearings, gears, various kinds of little gadgets of the sort that you find if you take apart present-day machinery and see what makes it work. After a while, you stop finding really new kinds of things, and that gives you a sense of what functional components are needed to do general-purpose operations. An engine of a car, the motion of a robot, and so on. So looking down that pathway, looking at tools, building tools, and asking what would constitute a really good set of tools, and using computational physics-based methods to examine what kinds of structures could function well, what they could do if you were able to build them with suitable tools. The conclusion is that remarkable results can follow from being able to make a box that might look something like this. And what that would contain is what can be thought of as factory-on-a-chip technologies, not organizing patterns of bits with digital processes, but using what are remarkably closely analogous in an abstract way, physical processes, to organize not the smallest bits of information, but the smallest bits of matter, which is atoms and molecules. Not individual atoms, by the way. You don't work with individual bits in a computer, you work with bytes, you work with molecules in these kinds of machines for various technical reasons, at least most of the time. So a technology that starts with simple atomically precise building blocks can, with atomically precise motions, put them together to make larger atomically precise building blocks. It can be put together by a bonding process, chemical bonding, to make larger blocks, and so on. And about 30 steps of that kind of process takes you from an atomically precise building block on a small scale to meter scale products. Now, where do you get atomically precise building blocks? The small ones. Well, pretty much anywhere. Oxygen molecules are, water molecules are. Take silicon dioxide and dissolve it so that you get dissolved forms of silica. You find chemical species in there, little atomically precise structures. Small molecules of particular kinds are atomically precise. And if you work with those and don't lose the precision, then the path from small structures to large structures turns out to work. You can analyze this in lots of detail from multiple directions. And the conclusion is that one can make devices that start with simple substances and make a very wide range of complex products. Much as you can start with ink and make patterns of dots, any pattern of dots you want. A simple machine with digital control can make any image. A cartoon, a page of text, a not entirely accurate rendition of the Mona Lisa. Very, an essentially unbounded range. The same is true, though with a very limited palette of materials and resolution at present, of 3D printing. You can think of this atomically precise manufacturing technology as being analogous to 3D printing, but taken much further in going to ultimate precision, very wide palette of materials, and high throughput. Precision comes from controlled molecular encounters. Digital precision comes from this digital precision, this atomic precision of the initial parts. But a key point is the processes can be fast. If you see a bird flap its wings, a regular bird, it goes flap, 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 or glides, flaps. A hummingbird will make an actual bit of a humming sort of noise if it goes by your ear. I was at Los Altos once and saw a hummingbird. Another hummingbird went and wham! Apparently males will slam into each other in midair as some sort of a competition. So you have to worry about aggressive uses of small things, birds or whatever. Well, you go down to a fly and it makes a buzz. Mosquito's wing makes a whine. If you were able to go much smaller, you'd find ultrasonic sound. And the reason is there's a fundamental mechanical scaling law which says that if you keep speed of motion constant, stress and material constant, mechanical deformation in the materials constant, the frequency is inverse to the size. And it turns out you can make machines with nanoscale parts instead of, say, the size that we see in conventional machinery. That's about a factor of 1,000,000. And a factor of 1,000,000 in size gives you a factor of 1,000,000 in frequency. Factor of 1,000,000 in frequency means that a device that can process its own mass in let's say a year at the macro scale has a roughly corresponding device. It's either 3 times 10 to the 7th seconds in a year, could process its own mass in 30 seconds. So that's a radical increase in productivity. There's nothing about working with molecules that makes the process slow. It makes it incredibly fast in terms of frequency. And if you have large arrays of devices, you can have high throughput. The molecules come in one end, they follow a contorted path as the assembly goes on, they come out the other end, they move at an appreciable speed. It takes a certain amount of time to get from one end to the other, and it's measured in minutes, is a typical number. Products, well, billion CPU laptop, roll of thin film high performance photovoltaics, components that plug together to make vehicles, a range of products that exceeds what we can make with modern industry because it exceeds the range of materials, exceeds the range of precision and control of the use of those materials, and essentially all dimensions you can think of. Clean production follows rather directly from this because you're not making things you don't want. It's not, cooking and burning and smoking and producing diffuse wastes. Resource consumption can be low. So I think that covers those points rather well. So I'd like to say a few words about the range of topics that I felt was needed to discuss in the book, which is, I think, the book's sort of reasonable lecture notes and this sort of about the book. So, I was going to warn you that I might read a few paragraphs. Okay, read a few paragraphs. This is, it calls for water. Yeah. The H2O, these are atomically precise 3-atom structures in here, about 10 to the 23rd per cubic centimeter. Imagine what the world might be like if we were really good at making things, better things, cleanly, inexpensively, and on a global scale. What if ultra-efficient solar arrays cost no more to make than cardboard and aluminum foil, and laptop supercomputers cost about the same? Now add ultra-efficient vehicles, lighting, and the entire behind-the-scenes infrastructure of an industrial civilization, all made at low cost, and delivered and operated with a zero carbon footprint. Low cost, well, let's see, simple low-cost materials, high throughput leads to low cost of capital, energy requirements are modest, labor approximately zero, and so on. If we were that good at making things, the global prospect would be not scarcity, but unprecedented abundance, radical, transformative, and sustainable abundance. We would be able to produce radically more of what people want and at a radically lower cost, in every sense of the word, both economic and environmental. This isn't the future most people expect. Over recent decades, the world has been sliding toward a seemingly inevitable collision between economic development and global limits. As nations expand industrial capacity, carbon emissions rise. Expectations of resource scarcity drive wars and preparations for war as tensions grow over water from rivers, metals from Africa, oil from the Middle East, and fresh oil fields beneath the South China Sea. Everywhere, progress and growth are beginning to resemble zero-sum games. The familiar expected future of scarcity and conflict looks bleak. these familiar expectations, the ones that drive politics today, the ones that drive the view of the future of young people today, many of whom don't see a future, these familiar expectations assume that the technology we use to produce things will remain little changed. But what if industrial production as we know it can be changed beyond recognition or replaced outright? The consequences would change almost everything else, and this new industrial revolution is visible on the horizon. Not only visible, but can be described in substantial detail, substantial from a systems engineering point of view, and quantified and critiqued. The story behind the ideas and, well, let's see, this gets us into another topic. I won't read this. I'll just look at chapter headings and comment on topics. This book covers everything I thought needed to be said, more or less, and so it should be a good basis for saying some things here. People asked me at the Oxford Martin School, the program on the impacts of future technologies, where I'm future technology that I've been at while I was working on the book. Fancy thing. And they would ask, well, what is the book about? And I said, well, I was writing about nanotechnology some time ago, and since then the topic has become very, very confused. And so the book is about that range of ideas and issues. And the purpose is to be very, 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 very clear about the topic, the structure, and some of the questions that it raises. The book raises more questions than it provides answers, as one might expect. Okay, so one angle of view is where the ideas came from. And so I say a bit about my background at MIT and aerospace systems engineering and the molecular sciences and how they were an inspiration for this. I should mention that Richard Feynman pointed very much in the same direction in 1959 in a talk he gave called There's Plenty of Room at the Bottom. And he took his inspiration from biological machinery as well. So then, to make this very concrete, I discussed the look and feel of the nanoscale world. Remember the animation of the gears and shaft and so on? Well, that looked an awful lot like a macroscopic machine. I mentioned scaling laws before. It turns out that if you understand that atoms are individually slippery, there are various interaction forces at surfaces, that structures of this size have size, mass, shape, strength, elastic properties, you realize, well, these are just small objects. And it turns out that the scaling laws are such that if you took a macroscopic machine with parts that move at, say, 1 meter per second, and a nanoscale machine that's similar material, say, with parts that move at 1 meter per second, a scale factor of 10 million, imagine the small one magnified by 10 million, slowed down, time magnified by a factor of 10 million, they would move at the same speed. They would have the same mechanical deformations. There would be the same accelerations, the same forces, and the same behavior. So there's been all this mystification about nano things and nanotechnology. It turns out that mechanical devices on this scale can be understood as being, aside from a bunch of very important details, but broadly speaking, can be understood as just small machines. And you can take your understanding of things and through the scale factor have an intuitive understanding that is qualitatively and quantitatively correct with respect to many aspects. So by making things very, very, very clear, part of my intention is to give people cognitive tools, information tools for thinking about these subjects and not taking other people's word from it, not necessarily believing everything they read on the internet, I hope. Except, of course, excerpts from the book, which should be assumed to be accurate until you really examine them closely and decide there's a flaw. One problem with this area has been that it's from wall to wall superficial implausibility. And if you read something that's novel, a lot of novel aspects, and say, well, this must be wrong, I'm trying to find out why, then you're reading it to find something that's wrong, and they say, okay, it's wrong. If, on the other hand, you approach it like a textbook, and you read something that seems wrong, instead you ask, what haven't I understood? And I very much hope that that's an appropriate approach to reading books which are based on, let's see, nanosystems, which I'll have a picture of earlier. It was based on my MIT dissertation, so it's sort of a textbook and should perhaps be approached in a learning fashion. Okay, another perspective, past revolutions. The agricultural revolution, well, it was a new way of making things, food. It's based on molecular machinery and biological organisms. The industrial revolution, new ways of making things based on machines, not entirely unlike, as I've been saying, the nanomachines that are relevant here. The information revolution, well, it's based on nanoscale components that work at high frequencies and that handle little discrete bits of something and organize them to make very general products. So there are a set of parallels in the nature of these three great past technological revolutions. And looking at surveying the similarities and differences is a useful way of framing atomically precise manufacturing and its implications. Not least, it gives a sense of the scale. If you imagine the Industrial Revolution, a couple centuries worth of that compressed, or the Information Revolution maybe on top of that and highly compressed but transposed into the world of matter, starts to give a sense. The Information Revolution, by the way, has many points in common, and in terms of economic considerations, there's a lot to be learned from the change in cost structure that has come with general purpose distributed machines that have very general ability to transform the things of their domain. Let's see, and then there's a discussion of, if you want to know how industry works and chemistry works and so on, at a certain level of abstraction, discuss that again for perspective. Chapter on science and the timeless landscape of technology, followed by one on comparing science and engineering, followed by one on what I outlined earlier, which is the use of physical calculation and engineering methods to explore the potential of future technologies. And it turns out that there is a lot of epistemic depth to these questions. The relationship between science and engineering is by and large very poorly understood in our society. Sometimes engineers will say that if a rocket works, that's a triumph of science. If it fails, that's an engineering problem. I come to the UK and I find that, as somebody was writing in a column in Nature, the word engineer refers to someone who will repair your lawnmower. Well, you know, there are many different levels and activities there. The key point is that none of them are science. Scientists take things in the natural world, use instruments to get information from them, use that information to give form to abstract descriptions of these things, and then they use those descriptions of nature, concrete physical descriptions, to constrain and shape general abstract theories. Engineers start with general abstract designs, concepts for whole families of potential aircraft, for example. They refine those designs into concrete physical descriptions and then use physical instruments, but they're manufacturing instruments, to take that information and impose it on nature. There's a parallel structure, but the arrows point in opposite directions. And the cultures are different. Scientists want to have small independent groups. Try to engineer a car with small independent groups. The parts won't fit together. Couldn't begin to make an automobile that way. And so there's a parable of the blind scientists and the elephant, and how you get a coherent picture of the elephant by having a lot of people looking at little parts and arguing. And then the same approach in science, in engineering, gets nowhere. And it's written to be rather precisely analogous to how nanotechnology has been pursued to date. It's been pursued in a scientific style. And part of the reason one has not seen large-scale, complex engineering results is that the funding has gone to scientists, mostly in material science, but others in the molecular sciences. The ones in molecular sciences, by and large, have not thought of themselves as doing nanotechnology, though they're working at the nanoscale with atomic precision. And they've worked as scientists, overwhelmingly distracted by concerns in biology, things in like aging and so on. And so we find the SENS people taking George Church and distracting him from his nanotechnology work to work on, yes, well, any event. As you might guess, I'm very pleased with the progress in biology, but taking some of the attention that has gone into understanding the atomically precise world of self-assembling components analogous to biology, and looking for systematic methods, ways of putting parts together to guide the motion of other parts, could go a long way, but it's outside the scope of the sciences as defined presently, in part because it's engineering. And part of what I am working on doing in this book is to make very clear what needs to be done to make more progress. And then the concept of exploratory engineering is also simple, but it's not exactly what people have done, except for the early space program. You know, the space program, the Russian space program began in Russia in the late 1800s. A man by the name of Konstantin Tsiolkovsky figured out the principles of rocket propulsion, figured out that oxygen and hydrogen were perhaps the best combination for propellants. They're used in upper stages today. And a whole lot of the requirements, quantitative requirements for space travel and space flight. So he became a, I don't know, hero of the Soviet Union or something like that after they let him out of prison. Interesting life. And became known as the founder of astronautics. And he did all of his work by presumably lamplight in rural Russia with pen and paper. His day job was that he was a school teacher. But he knew physics, and he could read what the chemists had found and concluded that, yeah, liquid oxygen, liquid hydrogen rockets, and later was explaining why multi-stage rockets were a good idea, could reach orbit. Here are the numbers. So there are precedents for this kind of application of physics to understand the potential of technology, enormous amounts of detailed information. Today we have computational modeling. Today we have engineering systems at the macroscopic scale that have analogs, potential analogs at the nanoscale. We've developed the methodology of systems engineering, the methodology of funded research laboratories. These didn't exist 150 years ago. And so on. And putting that into gear with the right focus will make a tremendous difference, in part because the progress in the fundamental technologies has been very large and largely unrecognized. So, as you might expect from being able to make concrete descriptions and from all of these analogies between macroscale and nanoscale productive systems, it turns out that the right way to organize an atomically precise manufacturing system looks almost absurdly like an automated factory. You need to move things around. Well, use conveyor belts. Have parts move from place to place. Well, you have a little device that moves a stream of parts from place to place. If you want to have really high-speed assembly of simple parts, you use what are known as continuous motion assembly machines. You'll find some YouTube videos of those. They're macro-scale machines that work at on the order of 100 cycles per minute. And all of those and the overall orchestration of motion can be imitated remarkably closely to work from the molecules up, given that you have the tools to make the right components and you solve problems rather than looking for more problems. Scientists look for problems to study. Engineers see problems and they say, let's try some other way of achieving our objective. Even polarized differently in what they think the importance questions are. So it's a very concrete description of potential systems. And products. So the purpose of the book is to discuss what matters to people, and I say, well, what can you build with atomically precise manufacturing? These kinds of materials and components. What can you make from these kinds of materials and components? Well, photovoltaics. Systems that transform, interconvert electrical energy and chemical energy efficiently. Lightweight structures for vehicles. More manufacturing systems. And then one can take these fundamental capabilities and ask, what can one expect that people would want to do with them? And this is now stepping one step beyond engineering. It's asking, given that people want to do the kinds of things they want to do, with these capabilities, what can we anticipate people doing unless they're stopped? Not saying anything in particular will happen, but saying that if technological progress continues along natural roads, here are some capabilities that will be met or exceeded. These are conservative assessments. The expectation is the capabilities will be exceeded, and that either capabilities will be used or there will be something that makes them not be used. Either way, they're a consideration in the world. And that leads to discussion of applications of all sorts. Let's see, I've not been showing my PowerPoint here. Applications, energy, transportation. Okay, clean water. This shows up on many discussions of critical questions for the 21st century. Well, what's clean water about? Well, it's sorting out the water molecules you want from others. That's done with membranes today. You can make better membranes. You can make better methods of cleaning the gunk off the membranes, lower the capital cost, increase the efficiency, provide inexpensive energy to do the thermodynamic work required to take water out of salt water, and so on. Let's see, I said something, I didn't mention information technologies, but one would guess that atomically precise devices might be useful in making very small digital devices. Nanotechnology is most practiced, but not called that, in the semiconductor industry. As a matter of marketing, all the chips, modern chips, could be called nanotechnology and would deserve that label at least as much as anything else in the world today. And industrial production, I think I've said enough. Well, low demand for scarce resources turns out to fall out for some more, lot of sort of specific reasons that I outline in the book. One can see how just as printing is now decentralized and customized, likewise, the production of high-grade industrial products could be likewise. There's a particular problem which I think that if you don't see it as very serious with potentially large risks, because climatologists really only halfway know what they're talking about, and if you don't see it as effectively irreversible, then you don't understand what's happening with CO2 in the atmosphere. There's a sense that a lot of people have that, well, you know, if you like sulfur dioxide goes into the atmosphere, you stop putting it in the atmosphere, it's gone pretty promptly. The problem goes away. In fact, SO2 in the atmosphere has been declining because of better pollution controls. There's a sense, either explicit or visceral, that if you turn off the supply of CO2 being poured in, that the CO2 levels will fall. Well, yes, but on a time scale of decades to centuries. It's different. Cutting back the rate of CO2 production reduces the rate of increase of a level that's already very high. So in the ordinary view of things, first of all, it's very hard to cut back or even stop the acceleration of the rate of emissions. And if you did that to an implausibly great extent, you'd merely have the rise slow. If you managed to have zero net emissions entirely, the climate would continue, the CO2 would remain high, and because of some geophysical lags, the climate would continue to warm for a while. And then the decline would be on a scale of decades. So here are some scenarios the IPCC had. You are there with the little mark there. It's a little bit above their worst case trend line. And the lowest case goes well beyond where we are, and so far it's been the high end. You'd like to be able to do that. To take the excess CO2 out of the atmosphere, get to liquid density, put it somewhere. And there are a lot of options for where to put it if you have this kind of manufacturing capability. The problem is that that is a project that seems to be a bit out of reach of our industrial technologies today within real-world constraints. The energy required is about 10 to the 21st joules. That's the thermodynamic minimum free energy work of compression to take dilute CO2 and compress the gas to liquid density. The power required to do that in 10 years is 3 terawatts. 3 terawatts is about the total electric power generating capacity of the world today. Gas-fired plants, coal-fired plants, nuclear power plants, hydroelectric, put it all together, throw in a pinch of geothermal, et cetera. An even smaller pinch of photovoltaics at this point. And that's 3 terawatts, and I don't think we're going to be doubling that capacity with zero carbon emission technologies, and then applying it to taking CO2 out of the atmosphere, which requires some additional equipment and goodies. It's a manufacturing problem, though. If you could make the requisite materials, the structures, you could build a system that would do that. It'd be about that big if you put all of the arrays in one place, and there's no need to do it. That much photovoltaic array, plus thermodynamically reasonably efficient mechanisms that can bind CO2 molecules and transfer them to a high-density reservoir, could draw down excess. It's the size of the rectangle. The circle there is to make it the square more visible. It's 200 some odd kilometers on a side for medium efficiency photovoltaics. That fits in the so-called empty quarter of Saudi Arabia, which I thought was a decorative place to put it. It's empty, right? In fact, small arrays could be tastefully put in places that are far, 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 far less environmentally obtrusive than agriculture. So again, people who understand this problem, I think, tend to get into a mode of despair. There's a way out. The way out is to take this line of progress, apply engineering methods, refocus, get a clear sense of objective. You don't get to the moon unless you try. This is a much smaller scale project in literal and other practical senses. And taken along this line further leads to atomically precise manufacturing. Ample energy and material resources for the entire globe to have a higher material standard of living than in the developed world today. Rapid drawdown of CO2 levels becomes feasible. Overall, sustainable global development. The long-term Malthus was right. It would be nice to keep that in mind, but in the time frame that people are ordinarily concerned with, sustainable global development of a sort that there aren't really good prospects for otherwise. And more generally, technologies that change prospects for the human future. And some resource books. I mentioned Nanosystems, which is if you like equations, it's a thick mathematical work of applied physics. It's the one that's based on the MIT dissertation. More recently, a technology roadmap that was done, managed by Battelle in conjunction with several of the US national research laboratories. I was the technical lead consultant and helped to give shape to it, so you can sort of guess. It starts with present laboratory abilities and looks down that road to atomically precise manufacturing. I think it's actually the first document that used the term atomically precise manufacturing. And then, much recommended is of course radical abundance. And I'd like to throw it open for questions, but first, I should mention, I read the first little bit. I should mention Appendix 2 is incremental paths to APM and describes all sorts of metrics and why it's a continuous path and management sorts of issues and a whole lot on how to get there, and it's relatively technical. But the last main chapter is addressed to readers and what I would like people to do that is actually within everybody's reach, because there are many different things that one can do that all matter. Everything from raising one's eyebrows in an appropriate context in a very serious meeting, to nodding at another appropriate context, through turning one's career in new directions and making amazing things happen in the world. What can one do to bend the arc of history and perhaps toward a better world? In the transitions ahead, and as always in human affairs, actions will lead to intended and unintended consequences, some expected and some not. Actions, of course, are shaped by perceptions, not only perceptions of facts, choices, and potential outcomes, but also perceptions of interests, of how to judge the outcomes themselves. There's a section, by the way, on prospects for security issues, which discusses a very serious pitfall that I hope will be avoided, which is that if you think about these technologies, you conclude, oh, they could be used for really dramatic strategic military advantage. But a competition to get there would be destabilizing And why would one want to have that advantage? Well, let's see. I suppose it would be to win a zero-sum resource game in the 21st century would be the major reason. So one does not want to use the technologies of radical abundance to prepare to fight a war over scarce resources that won't be scarce. So major message is have coherent scenarios. Don't, start thinking about the possibility that the future will look very different. And don't mix the scenarios. It's a different future. National interests are different in that context. Military strategies should be different in that context. And one needs to have two tracks of thought. And that has implications for near-term decisions as one begins to take actions that reflect some consideration of the possibility that what's discussed in this book might be somewhat correct. Okay, so perceptions of interests. And yet a further step back, perceptions are shaped by shared opinions that emerge from conversations in homes, offices, and conferences, in journals, books, and editorials, in blogs and online discussions. What we do and don't say matters in every sphere of life, and by our choices of what to say, all of us can help to shape the conversation that shapes the perceptions, that shape the actions that in the end shape the world. And for this audience, some people who have read Engines of Creation, and maybe people who have been very excited by these ideas and would like to give them a push. And I wrote a little piece here, which actually was I gave an interview for NPR's book interview series, and the interviewer actually read this part. So it's titled About Enthusiasm. There's something that I feel I must say to some of my readers, and I hope that they will understand a somewhat counterintuitive message and take it to heart. If you find these ideas about prospective technologies compelling, convincing, and exciting, if you imagine vistas far beyond any I've outlined, it's a very mundane book, as much as I can manage it, far beyond any I've outlined, or see solutions to urgent problems, and feel an urge to share the full measure of your excitement, then please lie down until the urge passes. In the world as it is, this kind of excitement triggers a negative response, and for reasons that usually make sense. Almost all grand ideas proclaimed by excited proponents turn out to be wrong and are generally discounted without consideration. If you want to make a positive difference, please help to keep fundamentals first. And this chapter is called Changing Our Conversation About the Future, and is about fundamentals that need to be kept in place to anchor the conversation. Keep fundamentals first. Help to correct mistaken ideas and join the conversation without shouting. And as for other readers, please help to keep enthusiasts grounded and remind everyone that feverish, misinformed people must not be allowed to set the agenda by provoking a backlash or by fostering a kind of guilt by association. To allow this would amount to granting such people the power to control the agenda, but with a minus sign. This has happened before and must not happen again. There's another chapter in here which is about the history of nanotechnology and how I had a Nobel Prize winner convince the world that I was utterly ignorant of the contents of my own dissertation, and that these factories actually involved little intelligent robots with fat, sticky fingers that couldn't possibly work. In the same issue of Scientific American, I think some pages earlier, I had said, there aren't any fingers. He then said, there are fingers, and that was taken to be a description of the ideas and a reason to dismiss them. That was a backlash against discussion in the 1990s, when popular culture went off into science fiction, and the scientific agenda with the label went off into material science. So that is why I felt compelled to write that. And then there's closing. Closing ought to be good for a closing, right? So I outlined some of the prospects of abundance, positive prospects. Will the outcome of the APM revolution in fact look anything like this? Understanding, confusion, choice, time, and chance will all have their say, and with a measure of wisdom, what follows may, in some measure, reflect our intentions. Outcomes aren't carved in stone, in part because human vision and choices are beyond prediction. As perceptions change, possibilities and politics change with them, while new media are transforming the discourse that shapes those perceptions. Unexpected new visions have again and again led societies in unexpected directions. towards surprising opportunities, problems, and sometimes solutions. As we sweep forward into the quickening rapids of history, will we find a safe course to a world worthy of the hopes of past generations? Neither success nor failure can be assured, but I am persuaded that our choices will matter. And the first choice that matters is what to say, and to whom, today. What is your plan? So perhaps they'll decide that they should buy the book for somebody. Anyway, so that is an outline of the contents, what I'm trying to achieve with the book. And thank you.
You mentioned that there's a vision of this abundance up there on the horizon.
Mm-hmm.
What role do you see for open innovation in realizing that vision? Do you see it as playing an important role?
Open innovation and the generalization of open source software, that kind of open?
Yeah, I mean, there was just the other day, I think in the MIT Technology Review, reference to some kind of true mini computer, about 2 millimeters squared, and that he dug into it. I mean, the key element in the bill of materials for that were all the licenses for all the technology that had to be bought in to enable that to happen. And,
Yes.
you know, beyond the science and the engineering to make these things available to market.
You don't want to get me. You don't want to get me talking about the patent system, the U.S. patent system in particular. Chinese patent system. Well, the purpose of patents is supposed to be to get people to share, at least one of the major purposes, to share information. You get a temporary monopoly over the use of some methods in exchange for sharing them with the world. Well, when generations of technology pass faster than the patent term, that starts to become a bit absurd. And the smoking gun is that my understanding is that in the software business, lawyers will tell people who are doing development, don't read the patent literature because then you get, I don't know, double or treble damages or something like that. And so they're specifically told not to learn from patents, when the purpose of patents is to learn from them, presumably, and that suggests that they are doing, if any, sort of the opposite of their job. Different fields of research are very different, and it's a complicated story. But with respect to open innovation, I expect that we will see a lot of it. I'm hoping to see a lot in the development of very concrete, number of technical reasons. The advanced systems are easier to design and model than the near-term systems. That's one of the disorienting, kind of confusing aspects about the area. Modeling becomes easier with advanced systems. Fabrication becomes easier with the harder to model near-term systems. So there's a lot of low-hanging fruit in open innovation on structures that can't be built yet, that can provide a very clear picture, quantitative and analyzed, publicly discussed, competitive games, so you can gamify some of these things, to understanding that advanced technology base. And with a little bit more difficulty, similar work can be done on some of the pathway technologies. If you look at David Baker's, the Baker Lab at University of Washington, they turned protein fold prediction into a successful game. And if you can do that, you can probably do a similarly good job with some of the engineering in the protein domain. It's called Fold It. You might want to take a look at it.
Nathan?
I'm interested in the economic pathway to atomically precise manufacturing. So, engineering is very much driven by economics.
Mm-hmm.
If you look at that progression from the rough blacksmith down to photolithography,
Mm-hmm.
each step of that process justified itself. It wasn't end stage driven. So there's a number of steps between where we're at now and atomic scale manufacturing. And what do those steps look like, not in technological terms as much as the market justification for them?
Yeah. Well, a first observation is that the path that's led from small molecules to the million atom scale has happened, and for many, many incentives, most of which are short-term, some commercial and some not. There's a reason why the non-commercial incentives have more, perhaps more traction in this area than some others, and that's because the science is what's called small science, in that it can be done with small teams, inexpensive equipment, and so on. So the short, direct answer to what you're saying, or relatively direct, is that this progress has been driven forward by short-term payoffs thus far. Continuing in this direction, tweaking the trajectory a little bit, one can expect continued spin-offs. Designing macromolecular assemblies that form larger structures is a core technology. Looks like there's a way of making flash memory equivalent devices that would have 1,000 times more capacity than what you'd get at the Moore's law limit, as one area where there seem to be a lot of ways of doing that, though not this year, but well short of the very advanced technologies. Applications in biomedicine are useful drivers in the engineering also, and that will clearly be continuing. At some point, some country, some nation or nations are going to say, yes, it's a lot more rewarding than going to the moon. It doesn't cost as much. Already spending billions of dollars, and it was largely because they got excited by my last book for a general audience. They just got confused on how to spend it.
Quite a few high staff. Roy?
You mentioned that you were concerned that a lot of the research funding has gone to materials science rather than to nanosystems and atomically precise manufacture. So what for you?
I may interject just briefly. The research that's being done is very valuable. I have no objection to the spending, to calling it nanotechnology and so on. My concern is not what was done, but what was left out. Excuse me. So it's good research.
What for you are the most encouraging projects that you can tell us anything about in this space then, in the atomically precise manufacture? Are there a couple of examples that we could go look at of people working on this?
What people are working on today is many areas of advancing the technology base, learning to make a wider range of atomically precise structures, largely folded polymers, some special inorganic material structures, a wider range of functional components, building a technology platform for molecular systems engineering. A case that I make in the book is that there is in fact a field of systems engineering that's really ripe for development now, because there are many different fields where people have made these parts. There has not been the cultural tradition, the funding structure to organize people to put the parts together. And right now we have frameworks on the 100 nanometer million atom scale. Protein engineering can make pieces that plug into specific slots on that. Other ways of doing that as well. They can be used to bind inorganic structures that people have spent a lot of money developing, little optoelectronic and electronic devices and sensors and so on. There's a prospect of being able to arrange hundreds of nanoscale components in 3 dimensions with atomic precision, essentially by refining technologies already in hand. So what I find most exciting today is people doing that refinement and beginning to put the pieces together. And I think the greatest promise is in doing that in a much more systematic and focused way.
Do you foresee a different change in the sort of macro level mix of raw compounds or raw molecules and atoms used in a nanotech future in comparison with today's technology? Do we rely less on iron and steel and more on silicon or in cobalt or on something else?
Very much so, and that's a topic that I focus on at some length, because it's very important in looking at the future of resources and the cost structure of a manufacturing technology of this sort.
Any sort of broad thing?
Yeah.
Read the book, Dean.
Oh, right.
You have to read the book now. I can outline that. I was saying they spend a lot on material science. I've been a great fan of material science since before I started the nanotechnology stuff. Engineers in material science tend to have a bit of a love affair. Look around, almost everything you see is mostly structural material. Cellulose, a little bit of ink, which does some optical things, but not a lot of ink. Structural things, the moving parts are structures with size and shape and some surface properties. A computer, most of a chip is structural. It's the substrate, a little bit of active material. And that applies to almost everything except maybe the guts of batteries and a few areas where you have a block of material that has some special chemical properties, just kilogram for kilogram. The best structural materials, if you can make them precisely, are ones with strong covalent bonds. They're materials like silicon, silicon carbide, diamond, graphite, graphene, aluminum oxide is very good, and mixtures of all of those in patterns, some of which are found in nature and some of which don't form spontaneously, but they're perfectly stable if you arrange the matter that way. So these make better materials, stronger, stiffer, more corrosion resistant. If you want to make these materials transparent, a lot of them in their natural ways of organizing them are also transparent. And so I was recently reading about the people wanting to vacuum up a bunch of Pacific seabed to get magnesium nodules, to get magnesium and cobalt and copper and manganese, yes. And if you ask what are those used for, all except for copper are primarily used as alloying elements for steel. But if you don't want to make steel, there's not much interest in them. And copper is a special case. It's not used structurally, it's used to carry current. And it just happens to be the case that one of these covalent materials, carbon nanotubes of the right kind, are moderately more conductive than copper and a lot lighter and stronger. So it turns out that you end up getting down to rare earth elements in magnets, special electronic properties there, but then it turns out you're not interested in using magnetic motors anymore because of scaling laws and other options. See catalysts, but if a catalytic center process does 1 million cycles per second, a gram of catalyst, roughly speaking, makes a ton of product per second. You don't need much platinum. The conclusion essentially is that almost all of the materials that are most valuable in this case are earth-abundant materials. That's just, doesn't come directly from atomic precision, but it falls out pretty rapidly. Oh, and the problem with the covalent materials is they're brittle. And if you make them big blocks with cracks, they don't exhibit their strength. If you can make carefully structured fibrous composites or materials like what you find in mollusk shells, laminates with other materials, then they're excellent. But that requires advanced fabrication, which this provides, and that's why the conclusion follows.
Good.
It was actually as an engineer, it was a more direct question. What's happened with Nano Engineer 1 and the Nanorex Corporation software, especially because it's meant to be open sourced, and I can find it on GitHub, but I can't seem to find if the attached license actually allows open collaboration is GPL or something.
GPL.
It is GPL.
It is GPL.
It's just the last commit, I think, to the source base was about 8 months ago, and it seems to be running on some very old libraries.
Yeah. So in the middle of the last decade, a visionary with some funds by the name of Mark Sims funded an open source project to develop Nano Engineer 1, which was actually the source of the animations and the structure that I showed. Those are both out of Nano Engineer 1. To provide a graphical user interface modeled on engineering CAD systems, computer-aided design for mechanical engineering. And also was used to develop tools for structural DNA nanotechnology in collaboration with a group at Caltech in particular that made some of the major breakthroughs there. What happened was that the financial crisis whacked the basis for it. Development therefore stopped, and essentially. And the code base was in the process of being changed. It had evolved from something that was picked up somewhere that was a very bad starting point. It was about to become good with a major rewrite and refactoring, and that's where it got cut. So I can't even recommend the code base as a starting point. But the purposes, a lot of the specific implementations, the strategy behind it, I would very much like to see a restart of a similar open source project. I think that could be very powerful.
I'd like to ask about timescales. I mean, what are the kind of timescales in which you think some of these advances that you're still looking for can take place?
Well, let's see. I like to be oblique about that, if you'll excuse me. see, the first thing to say is that you can't calculate timescales. They have to do with human action and all of the peculiar things that happen in politics and popular culture and gaps in funding and focus in funding make enormous differences. After a talk that I gave at Oxford, another structural DNA nanotechnology engineer said, well, how long do you think that this is likely to take? And I said that I expect that it will, I think that it will happen faster than I expect. and then I asked him, does that, it's paradox, does that convey something? He said, I think it does. Let's see, another oblique answer which speaks to policy and importance is I think that one is almost certainly going to get to the key thresholds before the oceans rise much higher and before the polar ice melt runs to some really thorough completion.
So we can relax.
So we can relax, yes. There are various points in the book where it says, don't count on this. In particular, not on a time scale. My personal sense, and I will not put a date on it, is that there is a tremendous amount of technology base that has not been explored and not an attempt to put it together. I think that when clever people start asking, how do we put these pieces together to make better tools, that some surprisingly fast progress with surprisingly short pathways will in fact turn up. And you said 3 to 40 years. 40 years sounds to me like a very, very long time in this context.
So I want to follow up on your answer because I've, of course, been for some time in a very similar position. People constantly ask me how soon technology is going to happen. And I take a different strategy personally, and I want to tell you why, and I want to ask you whether you think there's a parallel.
Please.
So I basically say that I think it is important for those of us who consider ourselves experts in this area to broadcast our best guesses as to timeframes and indeed costs, for that matter. Simply because if we don't do that, then people who are less informed are going to come to their own opinions, and those opinions are probably going to be wrong, either vastly too optimistic or vastly too pessimistic, but in either case, the long run is going to work out less well. And I've been in running battles with mainstream gerontologists for at least a decade in respect of exactly this, because I've pretty much stuck to my guns in this. I'm wondering whether there is a difference between molecular manufacturing and the biology of aging in this regard, or whether there's a parallel. I mean, it seems to me that if the amount of money that would be taken and the amount of time that would be taken are of the same order in your estimate, in your best guess, then the same argument ought to apply. And in my case, the order is, I tend to say that I think we've got a 50-50 chance of getting to a point where nobody can argue that aging can be brought under genuine biomedical control within about 10 years, given only about $100 million a year of funding. So all the numbers in, the time, the money, and, my estimate of success. If you had to give a best guess, would the numbers be about the same?
Well, I think you have a very good parallel there, and I think your strategy makes a lot of sense in that context, and that a similar strategy, I think, makes sense in my context, but perhaps not this month or this year. But you said a certain amount of money and a certain amount of time for nobody to be able to argue that one cannot achieve large results.
Because, I mean, if one puts numbers on it, then one is persuading people with those resources at their disposal to actually concentrate minds rather than just say, well, I can't think about this.
My stance is that if you get 5 decently competent physicists together with me to make sure they don't go down in the same room without to sort of answer questions that they might otherwise get stuck on, and say, we would like your opinion, and we will take that as a reasonable indication of whether this makes sense, that could be done approximately 2 weeks after someone convened the group with a couple of weekends. Because what you're looking at involves new science. You have to make scientific discoveries. You do have a sense of what kinds of discoveries can be made in these areas, but not the details, of course, which is consistent with what I was saying. There are some predictions and expectations one can have. And what you're doing is engineering, but it's engineering in an area where the complexity and the tools are hard to define. Engineering approach works, but you can't sit down and say, we're going to do a computer simulation. You know, just that would be, anybody who tried to do that in your area, except in some very limited domain, I suppose maybe would be being silly. So they're very different qualitatively. And as I say, this is an area where one can sit down and check the numbers. Been laid out, check the numbers. If there are some numbers that you don't like, well, do a sensitivity analysis. And if you think there's some part that doesn't work, well, you probably haven't read the right paper yet. And let's talk about that. So my view is that the problem is that people have not understood that there is something to understand. I need to find a better way of phrasing this. My case isn't that this general picture is accurate. It's that it's accurate and demonstrably accurate, and if it's not demonstrable, then I'm wrong. It's not that I'm wrong if this isn't true, it's that I'm wrong if it isn't true and demonstrably true given reasonable inspection. In other words, if one invests the time to make a decision, a low amount of effort can in fact get the information that in your area you're saying would take, was it 10 years, $100 million. So in that sense, I could say, hey, get to Aubrey's threshold for a minute fraction of the money and a minute fraction of the time, because it's an entirely different question, really.
With the key people involved.
Yeah, yeah.
Okay.
But then in terms of time and pathways, which is much more directly analogous to what you're saying, I think your strategy, the kinds of things you're saying are exactly right. And with little modification on thresholds and transposing, I think similar times and numbers is what I would be inclined to quote.
I have a few more questions before we move to the book signing. So you've had your hand up for a while, yes?
I'm interested in the carbon capture example. So you mentioned that we need 3 terawatts of power over 10 years.
Mm-hmm.
Is that applying APM technology to the solar cells as well as to the actual carbon capture technology? Do we need to apply it to both? Or is it more a case of applying it to one or the other?
Okay. In terms of coherent scenarios, which this is related to, coherent scenarios essentially say that you move along doing relatively small-scale molecular things, special case materials things, maybe some electronics applications like the memory application, and that these are important from time to time important on a conventional scale of science and technology and industry. That there is a threshold at which an overhang of modeling and the increasing tractability of the engineering medium leads to making systems that are scalable. If you can make the right kind of small system, micron scale, you can make an array of them. The array can produce little building blocks that can be put together by simpler, larger machines. It just seems to be a not sharp, but fairly sharp threshold. So on the other side of that, just natural to say, how would one use this technology for all of the parts under consideration? That said, the assumptions on photovoltaics, because I'm very conservative about these things, were pretty much comparable to what you find being made today in terms of efficiency. The assumption regarding the carbon capture was that one can get reasonably thermodynamically efficient, and I can see ways of doing that, but the ways I have in mind use atomically precise, fancy little gadgets. And another general principle is, I will say, such and such can be done with APM, and someone else says, you don't need it. I'll say, you're probably right, tell me.
There's a question in the row behind. Yes?
Just from an English perspective, you mentioned Oxford. I wondered whether Professor Peter Dobson was appreciative of the work you're doing and taking a similar view to your microeconomics and being quite reserved about setting timescales. I'm one of the people that gets fundings for these sort of arrangements. He says, yes. I'm working on a microeconomic scale within an environment that's politically unsound, I would say, for scientific advancement. So I just wondered how you see sort of the English-British perspective.
Well, first of all, I need to speak with Peter Dobson. I've had my head down while working on the book, and I'm sort of just now getting out and actually talking to people at Oxford after being there for over a year. By the way, my intention is to be in the UK long term. I've ironed out visa considerations, so that's going to be straightforward, which I guess says something about my perspective on Britain. Part of that is because of Britain is, punches above its weight, as they say, in science and technology. It's said to be less good at translating these developments into industrial applications, but that's less important in moving down an inexpensive path toward a large goal that is kind of outside the usual industrial frame. And Britain at the moment is sort of kind of part of the EU. And the flying distances are less, and it seems to me to be a good place to stand for international, connections with the international science community. I have ties in the U.S. and, would like to broaden those. And also, I think the EU and China are less likely to fly at each other's throats, which may be important.
Brian?
Eric, after reading the book and going back, diving deep back to the 1981 paper and looking through engines of creation and going through all this different stuff, I certainly have way too much to ask. Oh, and then I didn't have enough time, so I put it on the audio reading, and I was just doing it while I was sleeping. So it's all as loaded in as much as possible. And there was just two little things. One was this quote I saw: finding a permissible stress level which will provide satisfactory service is not difficult. Competition forces search for the highest stress level which will still permits satisfactory service. This is more difficult. I didn't really understand what it meant, because at the time I thought it was about customer service, and I thought in the future it'll be so bad, the customer service, that we're just at a maximum level of stress.
Yeah.
But the real question is a simple one, and that is, when you wrote about the manufacturing of, I think it was a car, how much time does, how much time does the assembly process require from end to end? And I'm going, all right, minutes, seconds, nanoseconds. And then you go, the outermost stage, and there's something that says maybe 1 minute. I'm not sure. So how long does the car take?
I try to keep things that sound outrageous and aren't terribly important in soft focus. By the way, people say it's very readable and enjoyable, so it isn't perhaps as boring as that might sound. Got a nice little review in Nature too. But let's say, so just rewinding a little bit. That quote was a quote from a handbook of machine design. That was, I thought, very apropos of the difference between precision, scientific precision, and engineers saying, well, we'll not optimize, we'll calculate conservatively, and okay, it's going to be heavier and more expensive than it needs to be, but it'll work, and let's solve another problem. It was an illustration of that. And service means, like this wheel will serve well in carrying our chariot forward or whatever. Yep. So in terms of the time required for making things by this kind of technology, I said that scaling of motion is implied that scaling with constant speed in meters per second is appropriate. And the reason you get twice the frequency at half the size, it's going half the distance per cycle. Well, just step back and ask. If you have small molecules coming in here, and you're not letting them just sit around doing nothing for a long time, no particular reason. They do that in the input container, the equivalent of the ink cartridge, big fat ink cartridge. If they're moving along, and you move at a slow speed to minimize energy dissipation, and millimeters per second or centimeters per second is rather slow. And they keep moving at constant speed, and the path isn't straight, it's a little convoluted, but if you're going to make an object that's meter scale, have a meter scale machine is adequate. Something is moving from one end to the other at speeds that are probably at least a centimeter per second. Well, how long does it take to get to the other end? Comes in as a molecule, comes out as a laptop computer with 1 billion CPUs. And let's see, it's hundreds of centimeters, a centimeter per second is hundreds of seconds.
2 minutes.
Yeah.
So literally.
So most of the interesting things are in soft focus in the book.
Well, it depends on what you're interested in. There is entirely. Let's just say I want to get the fundamentals really solidly in place.
Right. Get the fundamentals right, and then you can do some Harvard Business Reviews or some tackle some of these really interesting questions as well.
That is what I've attempted to do.
Right. So I'm going to take a couple more questions. There was one over here. Yes.
Hi. I'll throw you 3 different topics and see if any of them appeal to you. The first one is, you haven't said anything about the sources of energy for the actual process itself.
Okay.
and that in comparison to current technologies would be an interesting topic. The
Yes.
second one is, you haven't mentioned food, which of course as a world resource is quite an important one.
Mm-hmm.
And it's not, GM isn't necessarily a popular route to go
Mm-hmm.
down. So, and the third one is your analogy with the, what I'd call sort of full-scale manufacturing is very much about mechanics of solids. You haven't mentioned fluid dynamics or anything to do with fluids, which maybe doesn't scale in the same way.
Yes.
So any of those?
Yes.
Or none?
I think I can attempt to address all of them briefly. Fluids indeed do not scale the same way. Viscous force, if you use sheared fluids and viscous forces, the natural scaling is not constant speed. Therefore, there are no fluid lubricated surfaces. It turns out, happens to be the case that one can do much better with atomically precise non-bonded surfaces moving over one another. And that's, details of physics, and oh yeah, it works very nicely. So the only important fluid flow is distribution of fluids to places where you then use them as a source for molecular building blocks at the interface between fluid flow and diffusion and the more deterministic mechanism. And that's viscosity isn't a big issue there. So fluids are different, and that's how the differences, which are problematic, are avoided in this context. With respect to food, what I outline in the book is the prospect of use of much more wide-scale use of enclosed agriculture. In typical climates, you can get more than a factor of 10 improvement in yield per hectare per year if you keep the humidity what it should be and keep the temperature what the plants like, and you fertilize them well, and you don't, if you enclose things properly, you also don't pollute the nearby streams with materials that will cause algae blooms and so on. So the conclusion is that if you could simply afford to build the structures, physical structures, pumps and so on, and make them easy to snap together so the labor to put things together isn't too high, you could increase the productivity of agriculture enough that you could perhaps free up a lot of land for maybe something other than monoculture, which as an environmentalist I think is highly attractive, and also have food independence in places where one might think it wasn't possible, including very high density areas and areas where there isn't a real prospect of farming under present climate and so on. So yeah, very conservative application. Many areas you could say it's a manufacturing problem. If we could make these things, we could use them to solve the problem. Agriculture is one. As for energy, same doing all three. As for energy, the energy required for these operations is a chemical level of energy. You're making and breaking bonds to process the small molecules and then put them together to make larger structures. A conservative estimate would say that the energy per kilogram is something like the energy per kilogram of smelting aluminum, which is one of the more energy-intensive production processes. Then if you ask, what is the energy requirement per unit of product? Well, it turns out that the amount of material, it's almost all structural, as I was saying earlier. The amount of material needed to make equivalent structures is much less, and so it turns out that the energy consumption per unit of function is actually lower than present manufacturing. So more common materials, lower energy requirement. If you want something that's strong and heavy, you fill the pore space with water.
It sounds like good news all around, actually. If I can be slightly enthusiastic.
Except for the expectation of massive economic disruption, the further tools, though we're already seeing enough of it, for pervasive surveillance. The ordinary nanotechnology is already doing a nice job of that. And the potential for touching off a risky, really, I have to use the word stupid, arms race. The argument is essentially that national interest is very strongly going to be towards stabilization in a turbulent transition. Domestic stability, international stability, and you don't want to create excess international turbulence. And it turns out that you have a strong interest in the domestic security of other countries, which I think speaks in favor of some of the arrangements that were not put in place but were seriously negotiated at the end of World War II.
So there was one hand over there, yes, for a while. Yes, thanks. And this will have to be the last one question. No smuggling 3 questions.
In the semiconductor industry, they have roadmaps to predict and to specify the, say, wafer sizes, line widths, which are very useful so that everyone can plan and have all the machines working together. Would such a roadmap be useful in the nanotechnology industry?
You've got a roadmap in there.
Yes, attentive listeners will notice that the answer is always, well, it's in the book. I did try to provide answers to the important questions that arise, and that is a very important one. International Technology Roadmap for Semiconductors, page 215. Yeah, road mapping is very important, and as in making systems engineering things work. And I will outline a marvelous conceptual aspect of the world, which I think is useful for understanding a number of fields. If an area of technology is advancing, or could advance, and it's an area of engineering where there are many pieces that have to go together. In the case of semiconductors, you have the light source for the short wavelength light, which has been one of the sticking points lately. The very precise steppers, making of the masks, materials and process steps. A higher dielectric constant insulator was a step that was kind of hard a while ago. Moving from aluminum to copper was hard, but it was a step done a while ago. And to make a new generation of chips requires that these pieces, these process pieces, and sometimes literal physical pieces, fit together. Now, let's say that you were in a world that didn't have this forward momentum and didn't have a roadmap, and you didn't know what other people were going to do. Well, should I invest millions of dollars in making a state-of-the-art wafer, a mask stepping machine to lay down the patterns across a wafer? If I'm not confident that the light source will be there and people will be making the masks, that would be tremendously risky. And so on for everyone else. So in the absence of a formal or informal roadmap, you don't have the coordination, the mutual expectations required for everyone to think that everyone else is going to do the job necessary to make their own part valuable. With that, you can have fast progress in many areas. Without that, you're really stuck. And that lack of a roadmap at present in the molecular sciences and the emerging field of molecular systems engineering, I think is one of the major points of friction that can be eliminated or greased fairly easily. We took a shot at it in the roadmap I pointed to. I think it's time for another round.